Tonight, we're going to talk about the closest star system to our Sun, Alpha Centauri. You've probably heard that it's our nearest stellar neighbor, about 4 light years away. That sounds close, right? In cosmic terms, it practically is close. It's the next star over. But here's what's going to change your perspective completely. When you actually understand what that distance means, when you look at the real numbers, when you comprehend the barriers that distance creates, you realize something sobering. We are more isolated than you ever imagined. And by the end of tonight, you're going to understand exactly why the distance to Alpha Centauri represents one of the most daunting challenges humanity has ever faced. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Alpha Centauri isn't actually a single star. It's a system. 3 stars bound together by gravity, orbiting their common center of mass in a complex gravitational dance that's been going on for billions of years. The brightest member is Alpha Centauri A. It's slightly larger and more luminous than our Sun, about 10% more massive, about 1.5 times brighter. If you replaced our Sun with Alpha Centauri A, you'd barely notice the difference. Earth would be slightly warmer. The Sun would look slightly larger in the sky, but life would continue, essentially unchanged. The second member is Alpha Centauri B. This one's smaller than the Sun. About 90% of the Sun's mass, about half the Sun's luminosity. If you replaced our Sun with Alpha Centauri B, Earth would be colder. The Sun would appear dimmer in the sky. You'd need to orbit closer to get the same amount of heat and light. But it's still a perfectly normal star, a main sequence star fusing hydrogen into helium in its core, stable and long-lived. These 2 stars, A and B, orbit each other in an elliptical path. At their closest approach, they're about 11 astronomical units apart. That's roughly the distance from our Sun to Saturn. At their farthest separation, they're about 36 astronomical units apart, farther than Neptune's orbit. The orbital period is just under 80 years. They've completed 1 full orbit since the end of World War II. They'll complete their next orbit around the year 2037. If you could somehow stand on a planet orbiting Alpha Centauri A, you'd see Alpha Centauri B in the sky as an incredibly bright star, much brighter than any star we see from Earth. At closest approach, it would be about as bright as 1/100th of our Sun, bright enough to cast shadows at night, bright enough to read by easily. You'd have a second Sun in your sky, though much fainter than the primary one. Then there's the third member, Proxima Centauri. This is the one that's technically closest to us, which is why it's called Proxima, meaning nearest. Proxima is a red dwarf, a tiny star compared to A and B, only about 12% of the Sun's mass, only about 0.17% of the Sun's luminosity. If you replaced our Sun with Proxima, Earth would freeze instantly. It's just too dim, too cool. You'd need to orbit incredibly close to Proxima to get enough heat, so close that you'd be tidally locked, always showing the same face to the star, one side in permanent daylight, the other in permanent darkness. Proxima orbits the AB pair at an enormous distance, about 13,000 astronomical units. That's about 0.2 light-years. At that distance, it takes Proxima roughly 550,000 years to complete one orbit around the central pair. It's been bound to this system for billions of years, but in all that time, It's only completed a few thousand orbits. The system is old, between 5 and 6 billion years old, slightly older than our Sun. Alpha Centauri was already ancient when our solar system began to form. Stars operate on timescales that make human history seem like an eye blink. Our entire recorded civilization is maybe 6,000 years, a tiny fraction of 1% of Alpha Centauri's age. And they'll outlast us too. In 5 billion years, our Sun will die, expanding into a red giant and consuming the inner solar system. Alpha Centauri will still be there. A and B will continue their dance for billions more years. Even Proxima, despite being a red dwarf, will outlive the Sun by trillions of years. Red dwarfs burn their fuel so slowly they'll be the last stars shining in the universe. They've been here longer than we have. They'll be here long after we're gone, and yet we can't reach them. Now, here's the key fact, the one that matters for our story tonight: the distance. Proxima Centauri, the closest of the three stars, sits 4.24 light-years from Earth. That's about 25 trillion miles. Alpha Centauri A and B are slightly farther, about 4.37 light-years away. These are the nearest stars beyond our Sun. Nothing else is closer. People have known about Alpha Centauri for thousands of years. Ancient astronomers in the southern hemisphere saw it. Ptolemy catalogued it in the 2nd century. The ancient Greeks knew it as part of the constellation Centaurus, the centaur. Arab astronomers observed it. Chinese astronomers recorded it. For most of human history, we thought it was a single star, one bright point of light in the southern sky. It wasn't until 1689 that Jesuit priest Jean Richaud, observing from Puducherry in India, noticed that Alpha Centauri appeared double through his telescope. 2 stars, not one, close together in the sky, orbiting each other. This was exciting. Double stars were rare discoveries at the time. Most stars appear single when viewed through telescopes. Finding a binary pair, 2 stars gravitationally bound, orbiting their common center of mass, was valuable for understanding stellar mechanics. Over the following centuries, astronomers tracked the orbit of Alpha Centauri A and B. They measured the positions carefully, year after year, watching the 2 stars circle each other. By the 1800s, they'd established the orbital period, just under 80 years. They'd calculated the eccentricity of the orbit, how elliptical it was. They determined the separation between the stars at various points in the orbit. All of this was done without knowing the distance to the system. They could measure angles and relative positions, but not absolute distances. That required parallax. In 1832, Thomas Henderson, a Scottish astronomer stationed at the Royal Observatory in Cape Town, South Africa, began making precise measurements of Alpha Centauri's position. He was trying to detect stellar parallax, the apparent shift in a star's position as Earth orbits the Sun. This shift is tiny. For even the nearest stars, it's less than 1 arcsecond. An arcsecond is 1/3600th of a degree, incredibly small. To give you a sense, if you hold a coin at arm's length, the width of that coin is about 1800 arcseconds. The parallax Henderson was trying to measure was less than 1 arcsecond, less than 1/1800th, the width of a coin held at arm's length. He observed Alpha Centauri for months, made hundreds of measurements, carefully tracked its position against the background stars, and he detected a shift, a tiny wobble as Earth moved from one side of its orbit to the other. But Henderson was cautious. maybe too cautious. He worried about errors, about instrumental issues, about atmospheric distortion affecting his measurements. He sat on his data for years, analyzing and reanalyzing, hesitating to publish. Meanwhile, in 1838, Friedrich Bessel, in Germany, published the first confirmed measurement of stellar parallax for a different star, 61 Cygni. Bessel's work was meticulous. He'd accounted for every possible error source, developed mathematical techniques to isolate the true parallax signal from noise. His measurement was solid, undeniable. When Henderson finally published his Alpha Centauri measurements in 1839, a year after Bessel, he confirmed what Bessel had shown. Stars were incredibly far away, much farther than anyone had imagined. Henderson's parallax measurement for Alpha Centauri gave a distance of about 4.3 light-years. Modern measurements, using much better instruments, give 4.24 light-years for Proxima and 4.37 for A and B. Henderson was remarkably close. His measurements were accurate to within a few percent, despite the primitive technology. The discovery of stellar parallax changed everything. For the first time, humans knew the true scale of the universe. Stars weren't just lights in the sky. They were distant suns, unimaginably far away, separated from us by gulfs of empty space. The nearest one, Alpha Centauri, was 25 trillion miles distant, 4.24 light-years, farther than anyone could travel, farther than anyone could even meaningfully imagine. That was in 1839, nearly 200 years ago, and we still haven't gone there. We haven't sent a probe there. We haven't communicated with anyone there, because as far as we know, there's no one to communicate with. We've learned an enormous amount about the Alpha Centauri system from a distance. We've measured the masses of the stars using Kepler's laws and observations of their orbital motion. We've analyzed their spectra, determining their compositions, their temperatures, their ages. We've discovered planets orbiting Proxima. We've calculated the habitable zones around each star, the regions where liquid water could exist on a planetary surface. We've modeled the stability of planetary orbits in the complex gravitational environment of a triple star system. All of this from 25 trillion miles away, using nothing but light. Photons that traveled for 4.24 years to reach our telescopes. We've never touched Alpha Centauri, never sampled its atmosphere or soil, never walked on any of its planets, never sent a robot to explore it. We're limited to remote observation, and that's not likely to change anytime soon. We've mapped the nearby stars extensively. We know what's out there, within 10 or 20 light-years. There are several dozen stars in that volume. Sirius, about 8.6 light-years away. Epsilon Eridani, about 10.5 light-years distant. Tau Ceti, about 12 light-years away. But Alpha Centauri is closest. It's the next star over, our nearest neighbor in the cosmic sense. If the galaxy were a city, Alpha Centauri would be the house next door. Except the distance to that house is 4.24 light-years. Let's talk about what that distance actually means. Not just the number. The implications. Light travels at about 186,000 miles per second. Nothing in the universe can travel faster. It's not a speed limit we haven't broken yet. It's a fundamental law of physics. The speed of light is absolute, constant, unchanging, everywhere in the universe. When you look at Alpha Centauri in the night sky, and you can see it if you're in the southern hemisphere, you're seeing light that left that star system 4.24 years ago. You're looking back in time, seeing the star as it was, not as it is right now in this present moment. If something happened to Proxima Centauri today, if it suddenly exploded or went dark or did something unexpected, we wouldn't know about it for 4.24 years. The information couldn't reach us any faster because nothing can travel faster than light. We'd just keep seeing the star as normal, watching light that left before the event occurred, unaware that anything had changed. This creates a fundamental isolation. We see the universe not as it is, but as it was. The farther away something is, the farther back in time we're seeing it. For Alpha Centauri, that's only 4.24 years, which isn't much on cosmic timescales. The star hasn't changed significantly in that time. But the principle is what matters. We're separated from everything beyond our solar system by time as well as distance. Now, let's think about traveling to Alpha Centauri. This is where the distance becomes truly sobering. The fastest spacecraft humans have ever built is the Parker Solar Probe. It reaches speeds of about 120 miles per second when it's near the Sun, using the Sun's gravity to accelerate. That's about 430,000 miles per hour. Incredibly fast by any earthly standard. If you could drive that fast on a highway, you'd circle the entire Earth in about 3.5 minutes. You'd reach the Moon in about 33 minutes. You'd reach Mars at its closest approach in just a few days. But space is big. Unimaginably big. And even at 430,000 miles per hour, the Parker Solar Probe would take about 6,700 years to reach Proxima Centauri. 6,700 years. That's longer than recorded human history. The Parker Solar Probe, launched in 2018, if it were actually headed toward Alpha Centauri, which it isn't, it would arrive around the year 8,718. By that time, human civilization would be utterly unrecognizable if it still existed at all. Technologies would have advanced through multiple revolutions. Everything about our current world would be ancient history. And that's using our fastest spacecraft. The Voyager probes, which are actually headed out of the solar system into interstellar space, are traveling at about 38,000 miles per hour, much slower than the Parker Solar Probe. At that speed, Voyager would take about 75,000 years to reach Alpha Centauri. 75,000 years ago, modern humans were just beginning to spread out of Africa. We were hunter-gatherers living in small groups. We had stone tools. We had fire. We had language, probably, though we don't know for certain. But we had no agriculture, no cities, no writing, no civilization as we understand it. Everything that defines modern humanity, everything from the invention of farming to the building of pyramids, to the development of science and technology, to the creation of the internet, all of it has happened in the time it would take Voyager to reach Alpha Centauri. The New Horizons spacecraft, which flew past Pluto in 2015, is traveling at about 36,000 miles per hour, about the same as Voyager. It would also take roughly 70,000 to 80,000 years to reach Alpha Centauri. These timescales are incomprehensible in human terms. No human mission could last that long. No spacecraft we can currently build would remain functional for that duration. The electronics would fail. The power source would run out. The structure would degrade from micrometeorite impacts and cosmic radiation. Long before reaching Alpha Centauri, the spacecraft would be dead, a piece of space junk drifting silently through the void. So clearly, we need to go faster, much faster. Let's imagine we could build a spacecraft that travels at 1% of the speed of light. That's about 1.86 million miles per hour. About 670 million miles per day. Absurdly fast by current standards. The fastest spacecraft we've built goes at about 0.007% of light speed. So 1% would be more than 140 times faster than our current record. But let's say we could do it. Let's say we developed some breakthrough propulsion technology, nuclear pulse propulsion, fusion drives, antimatter engines, something that could accelerate a spacecraft to 1% of light speed. At that speed, the trip to Alpha Centauri would take 424 years, still longer than the entire history of the United States, longer than any nation-state has existed in its current form. But at least it's within the realm of conceivable human timescales. You could potentially design a multi-generational mission, a colony ship carrying thousands of people, designed to be a self-sustaining habitat for centuries. The people who departed Earth would live their entire lives on the ship. They'd have children who'd also live their entire lives on the ship. Those children would have children, and so on, for multiple generations. They'd have been born in space, lived their whole lives in space, never seen Earth except in historical records and simulations. They'd arrive at a destination their ancestors chose, undertaking a mission they inherited, not one they selected themselves. This creates profound ethical questions. Is it right to commit unborn generations to a journey they didn't choose? Is it fair to raise children in an artificial environment, knowing they'll never experience a planet's surface, never breathe unprocessed air, never see a natural sky? What if something goes wrong? What if the ship fails halfway there? What if the destination turns out to be uninhabitable? The people on the ship would have no way back, no way to abort the mission. They'd be committed, absolutely. And even if everything went perfectly, even if the ship remained functional for 4 centuries and the crew maintained their culture and purpose across multiple generations, you're still talking about a one-way trip. Communication with Earth would be nearly impossible in any practical sense. Radio signals travel at the speed of light. So, any message from the ship would take 4.24 years to reach Earth. Any response from Earth would take another 4.24 years to reach the ship. That's a round-trip communication time of 8.5 years. You could ask a question and be old or potentially gone before receiving an answer. Your children might be the ones to hear the response. By the time Earth's reply arrives, the situation that prompted your question could have changed completely. The ship might be dealing with entirely different problems. The people asking the question might not even be alive anymore to hear the answer. You'd be exchanging messages across time, like letters between distant eras. The ship and Earth would drift apart culturally, developing separately, evolving their own customs, their own languages, their own ways of thinking. Within a few generations, they might barely understand each other. The mission might continue, but the connection to Earth would become increasingly abstract, a historical footnote rather than a living relationship. Now, let's go faster. 10% of light speed. About 18.6 million miles per hour. At this speed, which would require truly revolutionary propulsion technology, maybe a fusion ramjet or a laser-pushed light sail, the trip drops to 42.4 years. Still, A long time. Still longer than most human careers, but short enough that a single generation could make the journey. You could board the ship as a young adult in your 20s and arrive at Alpha Centauri in your 60s. You'd be old when you arrived, but you'd have made the journey yourself, seen the destination with your own eyes, completed the mission you started. This seems more achievable psychologically. People have undertaken long-term projects before. Scientists have spent entire careers working on single experiments. Explorers have spent years traveling to remote locations. 42 years is a long time, but it's within the span of a single human life. But even at 10% of light speed, you face enormous engineering challenges. At that velocity, hitting even a tiny piece of space debris, a grain of sand, would be catastrophic. The kinetic energy would be immense. A 1-gram particle, about the mass of a paperclip, hitting your ship at 10% of light speed would release energy equivalent to about 43 tons of TNT. About 3 times the energy of the bomb that destroyed Hiroshima, from a single grain of sand. You'd need shielding, massive amounts of shielding. Some designs propose a large shield in front of the spacecraft, made of dense material to absorb impacts. But that adds mass, which makes acceleration harder. Other designs suggest using magnetic fields to deflect charged particles. But not all debris is charged. Some of it is neutral, unaffected by magnetic fields. You'd need multiple layers of protection, redundant systems, constant monitoring. Even then, a lucky hit from a larger piece of debris could destroy the entire mission. And you're traveling through mostly empty space, but not completely empty space. The interstellar medium contains gas and dust. Very thin, maybe a few atoms per cubic centimeter on average. But at 10% of light speed, even that creates problems. Each atom you hit transfers momentum. Over time, this creates drag. It slows you down. Not much, but enough to matter over 4 decades of travel. You'd need to account for this in your fuel budget. You'd need more propellant to maintain speed. And propellant is mass. More mass means more energy needed for acceleration. It's a compounding problem. The rocket equation is brutal. Every kilogram of payload requires multiple kilograms of fuel to accelerate it. And you need fuel to accelerate the fuel, which requires more fuel. It scales exponentially. Current chemical rockets can barely achieve 1% of their mass as payload. For every kilogram of useful spacecraft, you need 99 kilograms of fuel. For interstellar missions, the ratios become absurd. To accelerate a spacecraft to 10% of light speed using conventional rockets would require fuel masses thousands or millions of times the payload mass. It's simply not feasible. That's why proposed interstellar missions use exotic propulsion methods. Nuclear pulse propulsion, where you detonate small nuclear bombs behind the ship and ride the shockwave. Fusion rockets, where you fuse hydrogen into helium and channel the energy into thrust. Antimatter drives, where you annihilate matter and antimatter, converting mass directly into energy. Laser light sails, where you use powerful lasers based on Earth or in orbit to push a reflective sail, accelerating the spacecraft without carrying fuel. All of these have problems. Nuclear pulse propulsion requires detonating thousands of nuclear devices. The engineering is straightforward in principle, but the politics are nightmarish. Treaties ban nuclear weapons in space. Even peaceful nuclear explosions would be controversial. Fusion rockets require sustained fusion reactions, which we haven't achieved yet, even in stationary reactors on Earth. Building a compact fusion drive for a spacecraft is far beyond our current capabilities. Antimatter drives require antimatter, which we can produce only in incredibly tiny amounts at enormous cost. Current production rates are measured in nanograms per year. You'd need kilograms, maybe tons. At current rates, producing enough antimatter would take millions of years and consume more energy than humanity generates in centuries. Laser light sails require massive laser arrays, perhaps thousands of individual lasers synchronized perfectly, operating continuously for years to accelerate the sail. Then, once the sail reaches interstellar space, you can't slow it down. The lasers are back at Earth. They can't push from the destination. You'd arrive at Alpha Centauri, traveling at 10% of light speed with no way to stop. You'd flash through the system in a few hours, taking measurements as you passed, then continue into deep space forever. Every propulsion method has fundamental limitations. Physics imposes hard constraints that engineering can't overcome. You can't exceed the speed of light. You can't violate conservation of momentum. You can't get energy from nothing. These aren't technological problems. They're laws of nature. Now, let's imagine we could somehow reach 20% of light speed, about 37 million miles per hour. The trip to Alpha Centauri would take 21.2 years. 2 decades. You could leave Earth in your 20s and arrive in your 40s. Still young enough to explore the new system, establish a presence, and begin meaningful work. This starts to feel almost achievable. But the problems we just discussed, debris impacts, interstellar drag, propulsion challenges, they all get worse. At 20% of light speed, a 1-gram particle releases energy equivalent to about 170 tons of TNT, about 13 times the Hiroshima bomb, from a grain of sand. Your shielding needs to be even more robust. Your fuel requirements go up. The engineering becomes more daunting. And you still have the communication problem. Messages to Earth take 4.24 years each way. By the time you arrive, you've been out of real-time contact with Earth for 21 years. Everything you know about Earth is at least 4 years out of date. More likely, by the time you arrive, it's 25 years out of date. The Earth you left will have changed dramatically. Politically, technologically, culturally. The people who planned your mission might be retired or gone. The governments that funded you might not exist anymore. The priorities that drove the mission might have shifted. You might arrive at Alpha Centauri, only to find that Earth no longer cares. The public has moved on. Funding has dried up. Your transmissions back home, describing what you found, might be received with indifference. Or Earth might have advanced so much in the intervening decades that what you're reporting is obsolete. Maybe they developed faster propulsion after you left. Maybe a second mission launched years after yours, using better technology, and arrived before you did. Maybe they solved the communication delay with quantum entanglement or some other breakthrough. You'd have sacrificed 21 years, traveling in a tin can through the void, only to find you've been superseded. This is the tyranny of the rocket equation and the light speed limit. They impose costs that scale brutally with distance. Every additional light year multiplies the difficulties. Let's talk about what you'd actually encounter on the journey. The space between here and Alpha Centauri. Most people think of space as empty, a void, nothing there. That's mostly true. Space is emptier than any vacuum we can create on Earth. But it's not completely empty. The interstellar medium, the material between stars, contains gas and dust. Very dilute. On average, about 1 atom per cubic centimeter. That's far more empty than any laboratory vacuum. By comparison, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. 25 with 18 zeros after it. Space has 1 atom per cubic centimeter. That's empty. But over the distance to Alpha Centauri, 25 trillion miles, you pass through an enormous volume. You accumulate exposure to that thin gas. At 10% of light speed, hitting even a single hydrogen atom transfers energy. Not much. A hydrogen atom has negligible mass. But you're hitting billions of them. Over 4.24 light years, the cumulative effect creates drag, small but measurable. Your spacecraft would slow down. Not much. Maybe a fraction of a percent over the entire journey. But enough to affect your arrival time, your trajectory, your ability to navigate precisely. You'd need to account for this in your fuel budget. Carry extra propellant to compensate for the drag, which adds mass, which requires more fuel. The compounding problem again. Then there's radiation. Space is filled with cosmic rays. High-energy particles, mostly protons, accelerated to nearly light speed by supernovae and other violent events. They're flying through space in all directions, constantly. When they hit matter, they cause damage. In biological tissue, they break DNA strands, cause mutations, increase cancer risk. Astronauts on the International Space Station are exposed to elevated radiation levels, about 50 to 200 millisieverts per year. Compare that to the average person on Earth, who receives about 2 to 3 millisieverts per year from natural background sources. The ISS astronauts get 50 to 100 times more radiation than people on the ground. And they're still relatively close to Earth. They're inside Earth's magnetosphere, which deflects some of the cosmic rays. They're shielded by the station's hull. They're there for months, not years. On an interstellar journey, you're exposed for decades. No magnetosphere to protect you. No planetary magnetic field deflecting particles. You're out in open space, bombarded constantly by cosmic rays. The dosage adds up. Over 20 years at 1/5 light speed, a crew member would accumulate radiation doses far exceeding anything considered safe. Hundreds or thousands of millisieverts. Enough to significantly increase cancer risk. Enough to cause radiation sickness if the dose rate spikes during a solar flare or passage through a high radiation region. You'd need shielding. Thick walls made of dense material. Water is good for stopping radiation. Hydrogen atoms absorb high-energy particles effectively. Some spacecraft designs propose surrounding the crew compartment with tanks of water. Dual purpose. Radiation shielding and water storage. But water is heavy. Every kilogram of shielding is mass. You have to accelerate and decelerate. It eats into your fuel budget. Alternative approaches involve magnetic shielding. Generate a strong magnetic field around the spacecraft to deflect charged particles, mimicking Earth's magnetosphere. This works for protons and other charged cosmic rays. But it requires a lot of power. You need superconducting magnets, continuous energy input, cooling systems to keep the magnets at cryogenic temperatures. All of that adds complexity, mass, points of failure. And magnetic fields don't stop neutral particles. Some cosmic rays are neutrons, uncharged. They pass right through magnetic fields. You still need physical shielding for those. There's no perfect solution. Every approach has trade-offs. You're balancing protection against mass, complexity against reliability, safety against feasibility. And you're making these decisions for a journey lasting decades, traveling through an environment we've never directly experienced, relying on models and simulations that might not capture every hazard. Then there's the psychological challenge. 20 years in a confined space, traveling through darkness. The stars don't move. At least, not noticeably. They're so far away that even traveling at 20% of light speed, the view out the window barely changes. You look at the stars, and they look the same as they did yesterday, last month, last year. No sense of motion. No landmarks. Just endless darkness punctuated by distant points of light. Earth is behind you, receding. Alpha Centauri is ahead, approaching. But neither looks different day to day. Earth just becomes a dimmer point of light, eventually indistinguishable from other stars. Alpha Centauri gradually brightens, but so slowly you don't notice unless you compare images months or years apart. You're in a state of suspended animation, metaphorically speaking, traveling through nothing, toward something, with no clear sense of progress. That takes a psychological toll. Humans need variety, stimulation, a sense of movement and change. We evolved in environments where walking for a day takes you to new terrain, new sights, new experiences. On an interstellar spacecraft, you're in the same place every day. The same corridors, the same rooms, the same people, for years. Isolation studies on Earth, simulating long-duration space missions, show that people struggle with this. Depression rates increase. Interpersonal conflicts emerge. Motivation declines. And those studies last months, maybe a year or two, not decades. There's no real data on how humans cope with 20 years in a confined space, completely cut off from the outside world, unable to leave, unable to abort the mission, just stuck. Some people might handle it well, others might not, and you can't know in advance. You can screen crew members psychologically, select the most stable and resilient candidates, but 20 years is a long time. People change. Circumstances change. What starts as a well-adjusted crew might fracture under the cumulative stress. And if that happens, if conflicts escalate, if someone becomes a danger to themselves or others, what do? There's no authority to appeal to. No police, no courts, no outside intervention. The crew has to handle it themselves. Develop their own governance structures, conflict resolution mechanisms, social norms. Essentially, create a micro-society in a box, traveling through space, isolated from all external support. That's a huge ask. Even 50% of light speed, which is staggeringly fast, probably impossible with any technology we can currently imagine, would take 8.5 years to reach Alpha Centauri. That's fast enough to make the trip in a single human timescale without multi-generational issues. But the energy requirements are monstrous. To accelerate even a small spacecraft to half-light speed would require energies comparable to humanity's total energy consumption for years or decades. and you'd need the same energy again to slow down at the destination, unless you plan to just fly past at relativistic speed, which limits what you can do scientifically. Most interstellar mission proposals involve flybys, not landings or orbital insertions, precisely because slowing down is so expensive energetically. You'd race through the Alpha Centauri system at an appreciable fraction of light speed, snapping photos and taking measurements as you passed, then disappear into the cosmic darkness beyond. The entire encounter might last hours or days, after years or decades of travel. Now, here's something else to consider. What happens when you actually arrive at Alpha Centauri? Assume you've made the journey. Decades in space. You're finally approaching the system. Alpha, Centauri, A, and B are growing brighter in your view. Proxima is visible as a distinct object now, not just a point of light. You're entering the system. What do you do first? If you're traveling at 10 or 20% of light speed, you can't stop. You don't have enough fuel to decelerate. You're going to flash through the system at enormous velocity. You need to plan your flyby trajectory carefully. Where do you want to go? Which star do you want to observe most closely? Do you aim for Proxima because it has planets? Or do you prioritize Alpha Centauri, A and B, because they're more similar to our Sun? You can't visit all three on a single pass. They're too far apart. Remember, Proxima orbits the AB pair at a distance of 13,000 astronomical units. That's about 0.2 light-years. If you're flying through at 20% of light speed, crossing 0.2 light-years takes a year. You could potentially visit Proxima first, then continue toward A and B. But your trajectory is fixed. You're not maneuvering. You're just coasting. Whatever path you're on when you enter the system is the path you stay on. So you need to choose. Most mission profiles would probably target Proxima because of Proxima b, the potentially habitable planet. That's the scientifically valuable target. You'd plan your trajectory to pass as close as possible to Proxima, maybe within a few million miles. Close enough to get good imagery. Close enough to analyze the star's spectrum in detail. Close enough to observe Proxima b directly. You'd have a few hours, maybe a day or two, depending on your exact speed and how close you pass. During that window, you take every measurement you can, photograph everything, record data continuously, analyze the atmosphere of Proxima b, if it has one, search for biosignatures, measure magnetic fields, detect radio emissions, map surface features. You're gathering decades worth of observations in a few hours. Then you're past. Gone. Racing away from Proxima, heading deeper into the system or out into interstellar space beyond. You transmit everything back to Earth. A data package containing all the images, all the measurements, everything you collected. It travels at light speed. Takes 4 years to arrive. Back on Earth, scientists receive the data. They analyze it. They discover whatever you found. Maybe there's life on Proxima b. Maybe there isn't. Either way, it's monumental. Humanity's first direct observation of another star system. First, close-up look at planets beyond our solar system. First search for life conducted in situ, not from 25 trillion miles away. But you, the probe, are gone. You've left the Alpha Centauri system. You're heading into the void beyond. Unless you have fuel to turn around, which you almost certainly don't, you're never coming back. You'll drift through the galaxy forever. just like the Voyager probes. A human-made artifact traveling through space for eternity. Maybe, billions of years from now, you'll encounter another star, thousands of light years from where you started. Maybe another civilization will find you, study you, learn that humans existed. Or maybe you'll just drift forever in darkness, never encountering anything. Just moving through empty space until the last proton decays and the universe goes dark. That's the reality of flyby missions. They're one way. You don't get to stay. You don't get to explore the system thoroughly. You flash through, grab what data you can, and disappear. To actually stop at Alpha Centauri, to enter orbit around one of the stars or one of the planets, requires deceleration. You need to cancel out all the velocity you built up during the acceleration phase. That means carrying enough fuel to brake, which doubles your fuel requirements, or more, because you have to accelerate the braking fuel along with everything else. The rocket equation strikes again. Some designs propose using the destination star as a brake. A magnetic sail could deploy as you approach, interacting with the stellar wind to slow you down. Or you could aerobrake through the upper atmosphere of a gas giant if one exists in the right position. Use atmospheric drag to shed velocity. Multiple passes, skimming the atmosphere each time, gradually slowing down. This works if there's a gas giant conveniently located. If there isn't, you're out of luck. All of these add complexity and risk. The mission becomes harder, more expensive, less likely to succeed. Most proposals stick with flybys precisely because they're simpler. No deceleration required. Just point and shoot. But a flyby feels incomplete. You've traveled for decades to reach another star, and you only spend hours there. It's like traveling across the world to visit a famous landmark and being allowed only a few minutes before you're ushered away. Frustrating. But maybe necessary. Maybe that's the best we can do, given the constraints. Now, let's think about the communication during the mission. You're traveling to Alpha Centauri. Let's say it's a crewed mission, not a probe. A generation ship carrying humans. You launch from Earth. The journey will take a century or more. For the first few years, communication is relatively normal. Well, not normal. There's a delay. As you move farther from Earth, light takes longer to reach you. After 1 year of travel, at 10% of light speed, you're about 0.1 light years from Earth. About 600 billion miles. Light takes 0.1 years to cross that distance. About 5 weeks. So messages from Earth take 5 weeks to reach you. Your replies take 5 weeks to reach Earth. Round-trip communication time is 10 weeks. Still manageable. You can have conversations, sort of. You send a question, wait 10 weeks, get an answer. Slow, but functional. After 10 years of travel, you're 1 light year from Earth. Messages take 1 year each way. 2-year, round trip. You ask a question, get an answer 2 years later. The information you're receiving is a year out of date. News from Earth is old news by the time it reaches you. After 20 years, you're 2 light years from Earth. 4-year round trip. You're farther from Earth than Proxima is. You're in deep interstellar space. The signals from Earth are weak. You need powerful antennas to detect them. And the content is increasingly irrelevant. What's happening on Earth 4 years ago doesn't help you much right now. Your situation on the ship is what matters. Your immediate problems, your crew dynamics, your system's malfunctions. Earth can't help with those. By the time they hear about a problem and send advice, the problem has either been solved or escalated into a crisis. You're on your own. After 50 years, halfway to Alpha Centauri, you're 2.12 light-years from Earth. Messages take 2.12 years each way. 4.24 years round trip. The same as the distance to Alpha Centauri. You're equidistant from your origin and your destination, poised in the middle of the Gulf. Messages from Earth are now less frequent. The people who launched your mission are old or gone. New generations have taken over. People who didn't experience the launch, who don't remember the excitement and optimism. For them, your mission is history, ancient news. They have their own problems, their own priorities. Your transmissions back are dutiful reports, status, updates, descriptions of the journey. Maybe some scientific observations of the interstellar medium, but nothing groundbreaking. You're in the least interesting part of the mission, between stars. Not at the beginning, not at the end. Just traveling. Public interest has waned. Funding has shifted to other projects. You're still going, still committed, still following the plan. But you're increasingly isolated from the civilization that sent you. After a century, when you finally arrive at Alpha Centauri, Earth is 4.24 light-years behind you. Messages take 4.24 years to reach them. You report your arrival. Describe what you're seeing. Transmit images of Proxima b, measurements of the stars, whatever you've found. And you wait. 4.24 years for acknowledgement. By the time Earth responds, by the time they say congratulations, you've been at Alpha Centauri for over 4 years. You've already explored the system as much as you can, made decisions about what to do next, possibly started colonization efforts if you find a habitable planet, possibly faced disasters if things went wrong. All of that happened before you heard back from Earth. Their response, when it arrives, is reactions to news that's nearly a decade old. They're congratulating you on an arrival that happened 8.5 years ago, commenting on discoveries you made years in the past. It feels disconnected, like letters from a distant relative you barely remember. Nice to receive, but not particularly relevant to your current life. You've moved on. Alpha Centauri is your home now, or will be, if you're staying. Earth is the distant past. A place you came from, increasingly abstract, increasingly foreign. Your children, born on the ship during the journey, have never seen Earth. It's just stories to them, historical accounts, images and videos from before they were born. They're children of space. They identify with the mission, with the ship, with the destination, not with Earth. Their grandchildren, born at Alpha Centauri, will have even less connection. Earth will be mythology to them, the ancestral homeland, far away, unreachable. They'll know it intellectually. They'll learn about it in school. But it won't feel real. How could it? It's 4.24 light-years away. They'll never go there. They'll never meet anyone from there in real time. They're Alpha Centaurians now, or Proximans, if they settle on Proxima b. a new branch of humanity. Genetically human, culturally divergent, separated from Earth by distance and time. This is what interstellar colonization means. Not expanding humanity, fragmenting it, creating isolated pockets that can't meaningfully interact, that drift apart over generations, becoming separate species eventually. Not biologically, at least not for thousands of years, but culturally, linguistically, socially, different peoples, sharing a common origin, but nothing else. That's the cost of the distance. Not just the travel time, not just the energy requirements, but the isolation it creates, the permanent separation of human communities. Once you go to Alpha Centauri and settle there, you're not coming back. Neither are your children. Neither are your descendants for countless generations. You've split from Earth permanently. That's a profound step, one we've never taken as a species. Even the most remote human settlements on Earth are connected. You can travel from anywhere to anywhere else. It might take time, but it's possible. A person in the Amazon can, in principle, travel to Tokyo. It's a long trip, but it's achievable within a human lifetime. Alpha Centauri is different. You can't travel back. Not unless we develop radically new technologies. You're committed, absolutely. And that changes the psychology, the social structure, the entire relationship between the colony and Earth. They're not parts of a single civilization anymore. They're separate, independent, isolated. Is that a problem? Maybe. Maybe not. It depends on your perspective. Some might see it as tragic. Humanity fragmenting, losing cohesion, drifting apart. Others might see it as natural, inevitable, the way species spread and diversify. There's no right answer. But it's something to think about before we send missions to Alpha Centauri. Are we comfortable with permanent separation? With creating communities that will diverge from Earth? With accepting that we'll never have a unified human civilization again? These are philosophical questions, not technical ones. And they matter as much as the engineering. Now, here's something that makes it even worse. We've been talking about the distance to Alpha Centauri as if it's static, as if the star system just sits there waiting for us to arrive. But it doesn't. Stars move. Everything in the galaxy is in motion, orbiting the galactic center. Our Sun orbits the center of the Milky Way at about 140 miles per second. That's about 504,000 miles per hour. Alpha Centauri has its own orbital velocity. It's moving relative to us. The component of its motion toward or away from us is called radial velocity. For Alpha Centauri, the radial velocity is about minus 13.8 miles per second. The negative sign means it's moving toward us. The system is getting closer. About 13.8 miles every second. That's about 50,000 miles per hour. In about 27,000 years, Alpha Centauri will reach its closest approach to our solar system, about 3.2 light years away. Then it'll start moving away again as it continues on its orbit around the galaxy. In about 33,000 years from now, it'll be farther than it is today. In several 100,000 years, it won't be our nearest neighbor anymore. Some other star, currently farther away, will drift closer and take the title. So if you're planning an interstellar mission, You can't just aim at where Alpha Centauri is now. You have to aim at where it will be when you arrive. You have to calculate trajectories, accounting for the motion of both the Sun and the target star. For a trip taking decades or centuries, the target moves considerably during your journey. You have to lead it, like a quarterback throwing a football to where the receiver will be, not where they are when the ball is thrown. This adds complexity to navigation. You can't just point your spacecraft at the star and accelerate. You have to plot a course through three-dimensional space, accounting for velocities and accelerations and gravitational influences from other bodies. You have to adjust your trajectory continuously during the journey. Small errors compound over time. A 1-degree navigational error at the start of the journey could cause you to miss the target by trillions of miles. You'd arrive at the right distance from Earth, but Alpha Centauri wouldn't be there. You'd be in empty space, surrounded by darkness, your mission a failure. And here's the other thing. The thing that makes the isolation even more profound. We've sent exactly 5 spacecraft on trajectories that will eventually take them out of the solar system. Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. All 5 are moving outward, traveling into interstellar space. But none of them are headed toward Alpha Centauri. They're going in different directions entirely. Voyager 1 is currently the farthest human-made object from Earth. It's about 15.8 billion miles away, about 159 times farther from the Sun than Earth is. It's officially in interstellar space. It crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, back in August 2012. It's out there in the space between stars, traveling at about 38,000 miles per hour. But it's headed in the direction of the constellation Ophiuchus, nowhere near Alpha Centauri. If Voyager 1 were aimed at Proxima Centauri, which it isn't, it would take about 75,000 years to get there. But it's not aimed that way. It'll never go to Alpha Centauri. It'll just drift through the galaxy forever, a silent ambassador from humanity, carrying the golden record with sounds and images from Earth. In 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese, 445. It won't stop. It'll just drift past. In the distant future, long after humanity is gone, Voyager might encounter another civilization. They might find it drifting through space, examine it, decipher the golden record. They might learn that a species called humans once existed on a planet called Earth. But Voyager will never reach Alpha Centauri. None of our spacecraft will. Not unless we send something specifically aimed that way with the intent to arrive. And we haven't. The farthest we've sent a spacecraft is to the edge of the solar system. The Voyagers are about 20 light-hours away. That's 0.0023 light-years. Alpha Centauri is 4.24 light-years, about 1,843 times farther. We've barely left our own neighborhood. We've sent robots to the edge of our yard. The next star is still unimaginably distant. Now, you might be thinking, what about communication? Could we at least talk to anyone at Alpha Centauri? Send and receive messages, even if we can't physically travel there? Sure. Radio waves travel at light speed. If there was someone at Alpha Centauri to talk to, we could exchange messages. We send a signal. It travels for 4.24 years. They receive it. They send a reply. It travels for 4.24 years back. We received their reply 8.4, 8 years after we sent the original message. That's a long conversation. You ask a question as a child and get the answer when you're starting high school. You send a message in college and hear back when you're 30. You inquire about something in your 30s and the response arrives in your 40s. It's conversation, technically, but it's not dialogue in any normal sense. It's more like leaving notes for future selves or exchanging letters across decades. And that assumes there's someone there. As far as we know, there isn't. We've looked. We've listened. The search for extraterrestrial intelligence, SETI, has been monitoring the skies for decades, listening for radio signals that might indicate technological civilizations. They've found nothing. No signals from Alpha Centauri. No transmissions from anywhere nearby. Either we're alone in our local neighborhood, or any civilizations that exist aren't broadcasting, or they're using communication methods we don't recognize. We've also looked for planets around Alpha Centauri, and we found some. Proxima Centauri has at least 2 confirmed planets. Proxima Centauri b, discovered in 2016 orbits, in what's called the habitable zone, the region where liquid water could exist on a planet's surface. It's about 1.3 times Earth's mass. It orbits its star every 11.2 days. That sounds fast. But remember, Proxima is a red dwarf, much smaller and dimmer than the Sun. To be in the habitable zone, you have to orbit very close. Proxima b orbits about 4.7 million miles from its star, about 5% of the distance from Earth to the Sun. At that distance, the planet is almost certainly tidally locked. One side always faces the star, one side in permanent day, the other in permanent night. The day side might be scorching. The night side might be frozen. Winds would howl between the 2 hemispheres, trying to equalize the temperature difference. And Proxima is an active star. It flares. Sudden bursts of radiation that could strip away a planet's atmosphere over time. Proxima b gets hit with these flares regularly. Whether it has an atmosphere, whether it has a magnetic field to protect it, whether it has liquid water, we don't know. We can't see the planet directly. We detected it through the radial velocity method, watching Proxima wobble slightly as the planet's gravity tugs on it. We don't have images. We don't know what it looks like. It might be habitable. It might be a barren rock. We can't tell from here. There's also Proxima Centauri d, discovered in 2022, orbiting even closer to the star, about 2.5 million miles out. It's smaller than Proxima b, only about a quarter of Earth's mass. Too close to the star to be habitable, probably too hot for liquid water. Alpha Centauri A and B might also have planets. We haven't found any yet, but that doesn't mean they're not there. Our detection methods are limited. We can only find planets that happen to pass in front of their star from our perspective, blocking a tiny amount of light, or planets massive enough to make their star wobble noticeably. Smaller planets, Earth-sized or smaller, orbiting at greater distances, are harder to detect. There could be multiple planets around Alpha Centauri, A and B, that we simply haven't spotted yet. Maybe one of them is Earth-like. Maybe one of them has life. We don't know. And we won't know until we look more carefully, or until we go there. That brings us to the proposals. The actual mission concepts people have developed for reaching Alpha Centauri. Because, despite all the challenges, Despite the immense distances and the brutal physics, people are thinking about this seriously. The most well-known recent proposal is Breakthrough Starshot. Announced in 2016, funded by Russian billionaire Yuri Milner and supported by physicist Stephen Hawking. The idea is to build thousands of tiny spacecraft, each about the size of a microchip, weighing only a few grams. You attach each one to an ultra-thin reflective sail, maybe a meter across, made of material only a few atoms thick. Then, you aim a massive array of ground-based lasers at the sails. The combined power of all the lasers, maybe 100 gigawatts total, pushes the sails, accelerating the tiny spacecraft. Within minutes, they reach 20% of light speed. Then, you turn off the lasers. The spacecraft coasts through space, traveling at a constant velocity. No fuel needed. No onboard propulsion. Just momentum. They'd reach Alpha Centauri in about 20 years. Once there, they'd take photos, record data, measure magnetic fields and particle fluxes, and transmit everything back to Earth using a tiny laser. The transmission would take 4.24 years to arrive. So, total mission time, from launch to receiving data, would be about 25 years. A single human generation. The people who designed the mission could live to see the results. That's the dream. In practice, there are enormous hurdles. Building the laser array alone would cost billions, maybe tens of billions. You need thousands of synchronized lasers, each one powerful, each one precisely aimed. The optics have to be perfect. Any distortion in the beam, and you lose efficiency. The atmosphere distorts light. You'd need adaptive optics to compensate. You'd probably need to build the array in space to avoid atmospheric interference entirely. Then there's the sail. It needs to be incredibly thin to minimize mass, but strong enough not to tear under the laser's pressure. It needs to be perfectly reflective. Any absorption of light generates heat. At 100 gigawatts of laser power, even a tiny fraction of absorbed energy would vaporize the sail instantly. Current materials aren't good enough. We're talking about engineering at the atomic level, designing structures only a few atoms thick that can withstand incredible forces without failing. We don't have the technology yet. We're making progress, but we're not there. And the spacecraft itself, the chip, has to carry cameras, sensors, a computer, power systems, communication equipment, all in a package weighing grams. Current technology doesn't support this. We can make microchips with impressive capabilities, but adding cameras and transmitters and power sources in that size and mass budget is beyond us right now. And even if you solve all the engineering problems, even if you build the lasers and the sails and the chip spacecraft, you still have the navigation problem. At 20% of light speed, you're covering about 37 million miles per hour. If your aim is off by even a tiny fraction of a degree, you miss the target by huge distances. You need precision on a scale we've never achieved. And there's no course correction. Once you turn off the lasers, the spacecraft is coasting. If it's aimed wrong, it stays aimed wrong. It flies off into empty space, and you never hear from it again. Plus, at 20% of light speed, anything you hit destroys you. A dust grain becomes a bomb. The spacecraft is so small, so light, that any impact will obliterate it. You're flying through space for 20 years, completely vulnerable. The odds of making it through unscathed are uncertain. Maybe good, maybe not. Interstellar space is mostly empty, but not perfectly empty. There's gas, dust, the occasional larger particle. Over 20 years and 25 trillion miles, you'll encounter something. Whether it destroys you depends on luck. Breakthrough Starshot is planning to send thousands of these tiny probes. The idea is that even if most of them fail, even if 90% are destroyed by impacts or veer off course or malfunction, the remaining 10% still give you data. It's a shotgun approach. Quantity over quality. Send enough probes and some will make it. That's the hope. But even if it works, even if the probes reach Alpha Centauri and transmit back photos and data, what then? You've proven it's possible to send tiny scouts at relativistic speeds. You've gathered scientific information about the nearest star system. That's valuable. But you haven't established a presence. You haven't sent humans. You haven't built anything there. The probes flash through the system, snap some pictures, and continue into the darkness. They don't stop. They don't orbit. They don't land. They're gone in hours, leaving the system as empty as they found it. Other proposals are more ambitious. Project Daedalus, designed in the 1970s by the British Interplanetary Society, proposed a massive fusion-powered spacecraft. Two-stage rocket burning helium-3 and deuterium in fusion reactions to generate thrust. The spacecraft would weigh about 54,000 tons. Most of that is fuel. The payload, the actual scientific instruments and equipment, would be only about 450 tons. Less than 1% of the total mass. The rest is fuel. Daedalus was designed to reach 12% of light speed. Travel time to Alpha Centauri would be about 36 years. It would fly through the system, taking measurements, then continue into deep space. No stopping, no slowing down, just a high-speed pass. The engineering required is staggering. Sustained fusion reactions. Something we haven't achieved on Earth yet in a useful form. Fuel pellets injected into the reaction chamber and ignited by electron beams, creating miniature fusion explosions 250 times per second. The exhaust, superheated plasma, channeled through magnetic nozzles to produce thrust. All of this has to work perfectly for decades. No failures. No malfunctions. In the harsh environment of space, bombarded by cosmic radiation, exposed to temperature extremes. And you'd need 50,000 tons of fuel. Most of it helium-3, which is extremely rare on Earth. You'd have to mine it from the Moon, or from the atmospheres of gas giants like Jupiter. That alone would require an enormous space infrastructure. Robotic mining operations on the Moon, or aerostatic collection platforms skimming the upper atmosphere of Jupiter, scooping up helium-3 and transporting it back to Earth or to a construction site in orbit. We're talking about an undertaking that would dwarf any engineering project humanity has ever attempted. Decades of preparation. Trillions of dollars in investment. International cooperation on a scale never seen before. And at the end of it, you get a one-time flyby of Alpha Centauri. Valuable, scientifically, sure. But not the beginning of colonization or exploration in any sustained sense. Project Icarus, designed in the 2010s as a successor to Daedalus, refined some of the engineering, improved fusion drive designs. better fuel choices. But the fundamental challenges remain. You're still talking about fusion propulsion, massive fuel requirements, decades-long journeys. You're still dealing with the rocket equation. You're still limited by the speed of light. Some proposals involve generation ships, massive spacecraft designed to sustain a population for centuries. You'd need artificial gravity, probably from rotation, closed-loop life support systems, recycling air and water indefinitely, agricultural systems to grow food, habitats large enough for thousands of people to live comfortably, raise families, maintain a society. The engineering is almost beyond comprehension. You're building a world, a mobile world traveling through space. It has to be self-sufficient. No resupply from Earth. No rescue missions if something breaks. Everything has to work for hundreds of years. Machines wear out. Systems fail. You need redundancy, spare parts, manufacturing capability to build replacements, a crew skilled in every conceivable type of repair and maintenance, and you need a stable society. People living together in a confined space for generations, governing themselves, resolving conflicts, maintaining culture and purpose. What happens if later generations decide they don't want to continue the mission? They didn't choose this. Their ancestors did. Do they have the right to turn back? To stop halfway and just drift? What if the ship fractures into factions? Political divisions, religious movements, conflicts over resources or authority. On Earth, people can leave. Move to another country, another city. On a generation ship, there's nowhere to go. You're stuck with everyone else. Forced proximity for centuries. That creates pressures we can barely imagine. And at the end, assuming everything works, assuming the ship holds together and the society remains cohesive and the destination is actually habitable, you arrive. 4 centuries after leaving Earth. The Earth you left is ancient history. The people who built the ship are long gone. The civilization that funded the mission has probably changed beyond recognition. You're on your own. Completely. Forever. No going back. The ship doesn't have fuel for a return journey. You're committed to making a life at Alpha Centauri or failing and going extinct. This is the reality of interstellar travel. Not the sleek starships of science fiction, jumping to warp speed and arriving at distant stars in days or weeks. The real version is slow. Agonizingly slow. Expensive beyond measure. Dangerous at every step. Isolating in ways that are hard to articulate. You'd be separated from the rest of humanity by distances that make real-time communication impossible. By time spans that erase cultural continuity. By challenges so severe that failure is more likely than success. And this is just to the nearest star. 4.24 light-years. The next star over. Imagine trying to reach Sirius. 8.6 light-years. Twice as far. Twice as long. Twice as expensive. Vega, 25 light-years. The Pleiades, 440 light-years. The Galactic Center, 26,000 light-years. Andromeda Galaxy, 2.5 million light-years. Each step multiplies the difficulty. Each additional light-year adds years or decades or centuries to the journey. At some point, it becomes absurd. At some point, the distances are so vast that travel, in any meaningful sense, becomes impossible. We might send robot probes, tiny scouts, like Breakthrough Starshot in Visions, fire them off into the cosmos and hope a few survive to transmit back data. But sending humans, building colonies, spreading across the galaxy like science fiction imagines, the distances make it almost unthinkable. Not impossible, necessarily. Not forbidden by the laws of physics. But so difficult, so expensive, so time-consuming that it might never happen. Even if we survive as a species for millions of years. Even if we develop technologies beyond anything we currently imagine, the distances might still be too great. The isolation too profound. Alpha Centauri sits 4.24 light-years away. You can see it from the southern hemisphere, a bright point of light in the constellation Centaurus. It looks close. It looks like you could almost reach out and touch it, but you can't. It's 25 trillion miles away, farther than your mind can truly grasp, separated from us by a gulf that current technology can't cross, that near-future technology probably can't cross, that might remain uncrossable for centuries or millennia. We are isolated, alone on our small planet, orbiting our sun, separated from the nearest stars by distances that dwarf anything in human experience. We've sent probes to the edge of the solar system. We've looked outward with telescopes. We've learned an enormous amount about the universe. But we've never left home. Not really. The farthest any human has traveled is the moon. 240,000 miles. About 1.3 light seconds. A tiny hop in cosmic terms. Alpha Centauri is 4.24 light-years. 128 million times farther than the moon. We went to the moon in 3 days. We could go to Alpha Centauri in, we don't know, decades at best. Centuries more likely. Maybe never. That's the truth about the distance to the next star. It's not just far. It's worse than far. It's isolating in a way that challenges our deepest assumptions about exploration, about expansion, about humanity's future among the stars. We look up at the night sky and see countless stars. We imagine traveling to them, exploring them, building civilizations around them. It's a beautiful dream, a compelling vision. But the distances are real. The physics is real. The challenges are real. And they're not going away. We can develop better technology. We can build faster spacecraft. We can find clever solutions to engineering problems. But we can't change the speed of light. We can't make space smaller. We can't wish away the 25 trillion miles between us and Alpha Centauri. The distance is what it is. Vast, empty, forbidding. And we're here, on Earth, looking out at the stars, knowing they're there, knowing they're unreachable in any practical sense. At least for now. Maybe forever. This isn't a pessimistic view. It's a realistic one. Understanding the true scale of the challenge, the true magnitude of the distance, is the first step toward appreciating what we have here. Earth is not just our home. It might be the only home we ever have. The only planet we can actually reach and live on and sustain ourselves. The idea that we can just leave Earth, spread across the galaxy, find new worlds when this one becomes uninhabitable, it's comforting. It's hopeful. But it might not be true. The distances might be too great. The barrier's too high. We might be confined to our solar system forever. Not because we lack ambition, or curiosity, or courage, but because the universe is big, unimaginably big, and we are small. That doesn't mean we stop trying. We should absolutely continue developing better propulsion systems, designing interstellar mission concepts, searching for exoplanets, listening for signals from other civilizations. All of that is valuable. All of that expands our knowledge and pushes the boundaries of what's possible. But we should also recognize the reality. The distance to Alpha Centauri, just 4.24 light-years, is a barrier that might take centuries to overcome, if we ever overcome it at all. And if we can't even reach the next star over, the one right next door in cosmic terms, then the galaxy as a whole is beyond us. The 100 billion stars of the Milky Way, the trillions of planets that probably orbit them, the potential life and civilizations that might exist out there, all of it might remain forever out of reach. We'll see them through telescopes. We'll study them from a distance. We'll learn about them indirectly, through light and radio waves and gravitational effects. But we might never touch them, never visit them, never walk on their surfaces, or breathe their air, or meet their inhabitants. We might be alone. Not because the universe is empty, but because the universe is too big for us to cross. The isolation is profound. It changes how you think about humanity's place in the cosmos. We're not explorers destined to spread across the stars. We're castaways on a tiny island, surrounded by an ocean too vast to cross, looking out at distant shores we can see but never reach. Let's think about what we'd actually gain by reaching Alpha Centauri. What's the scientific payoff? What would we learn that justifies the enormous cost and risk? First, we'd get direct measurements of the system. Up-close observations of the three stars. Their magnetic fields, their stellar winds, their surface features. From Earth, we see Alpha Centauri as points of light. Even our best telescopes can't resolve surface details. We can measure spectra, track orbital motion, detect planets through indirect methods. But we can't see the stars themselves as disks with features. A probe at Alpha Centauri could change that. It could observe the stars from close range, map their surfaces, study their atmospheres. We could learn about stellar physics in ways we can't from 25 trillion miles away. Compare Alpha Centauri A and B directly to our Sun. They're similar stars. Understanding how they differ, how they're the same, would refine our models of stellar evolution. Then there's Proxima, a red dwarf, the most common type of star in the galaxy. About 70% of all stars are red dwarfs, but they're dim, hard to study from a distance. Proxima is the nearest one, the easiest to reach if we're going to study any red dwarf up close. We'd learn about how red dwarfs work, how they produce energy, how their magnetic fields behave. Red dwarfs are important because they're long-lived. They burn their fuel so slowly that they'll outlast every other type of star. Trillions of years from now, when all the massive stars have died, when even stars like the Sun have burned out, red dwarfs will still be shining. They'll be the last stars in the universe. Understanding them is understanding the far future of the cosmos. And there's Proxima B, the planet. Potentially habitable. From Earth, we've detected it indirectly. We've measured its mass, its orbital period, its distance from the star. But we don't know what it looks like. Does it have an atmosphere? What's it made of? Is there water? Are there oceans, continents, weather systems? Is there life? A probe could answer these questions. It could take photos, high-resolution images showing the planet's surface. It could analyze the atmosphere spectroscopically, looking for chemical signatures of life. Oxygen, methane, complex organic molecules. It could measure the magnetic field, if one exists. Search for radio emissions, natural or artificial. Look for any sign that we're not alone. That would be monumental. Finding life on another world would change everything. It would answer one of humanity's oldest questions. Are we alone in the universe? If we found life on Proxima b, even simple microbial life, it would prove that life isn't unique to Earth, that it can arise elsewhere, under different conditions, around different stars. That would suggest life is common. If it happened twice in the same tiny region of space, Earth and Proxima Centauri, both within a few light years of each other, then it's probably happened countless times across the galaxy. We'd know we're not alone. Even if we can't reach the other life forms, even if we can't communicate with them, we'd know they're out there. That changes our perspective, our sense of significance, our understanding of our place in the cosmos. But here's the problem: the cost. Sending a probe to Alpha Centauri, even a tiny one like breakthrough starshot envisions, would cost billions, maybe tens of billions, for uncertain returns. Maybe we find life. Maybe we don't. Maybe Proxima b is habitable. Maybe it's a barren rock. We won't know until we get there. And getting there takes decades and enormous resources. Is it worth it? That's a value judgment. Different people will answer differently. Some will say, yes, absolutely. The knowledge gained justifies any cost. Understanding whether life exists beyond Earth is worth whatever resources we have to spend. It's the most important question we can ask. Others will say no. Tens of billions of dollars could solve problems here on Earth. Feed the hungry, house the homeless, cure diseases, combat climate change. Why spend that money on a probe to a distant star when we have urgent needs here? Both perspectives are valid. There's no objectively right answer. It depends on your values, your priorities, your vision of what humanity should be doing. But here's what we can say definitively. The distance to Alpha Centauri makes everything harder. If it were closer, if it were 1 light year away instead of 4.24, the mission would be 4 times easier. 4 times faster, 4 times cheaper, 4 times less risky. Still difficult, but more achievable. If it was 0.5 light years away, 10 times closer, the mission would be 10 times easier. We could send conventional spacecraft, chemical rockets, maybe, or ion drives, technologies we already have. The journey would take years instead of decades or centuries. The engineering challenges would be manageable. We'd probably have done it already. But it's not closer. It's 4.24 light years, 25 trillion miles. And that specific distance, that specific gap, makes all the difference. It's right at the edge of what might be possible with radical future technology. Far enough to be prohibitively difficult with current technology. Close enough to be tantalizing. If Alpha Centauri were 10 light years away, we probably wouldn't even be having this conversation. It would be obviously out of reach. Nobody would seriously propose missions there. If it were 1 light-year away, we'd probably be planning missions right now. Multiple space agencies would be designing probes, developing propulsion systems, preparing launch campaigns. But it's 4.24 light-years, right in the middle. Close enough to think about. Far enough to be nearly impossible. That's frustrating. It's the difference between having a goal that's achievable with effort and having a goal that might be forever out of reach. And we won't know which it is until we try. Or until we give up. That's sobering. It's humbling. But it also makes this island, this Earth, infinitely more precious. If this is all we have, if this is the only world we'll ever truly inhabit, then we'd better take care of it. We'd better solve our problems here. Climate change, resource depletion, conflict, inequality, all of it matters more if there's no backup plan. No escape hatch to another world. No frontier to flee to when things get difficult. We're here. This is home. And the distance to the next star, to Alpha Centauri, to anywhere else, is worse than you think. Think about our cosmic neighborhood for a moment. The region of space within 10 light-years of the Sun. How many stars are there? About 14 star systems. Some are single stars, like our Sun. Some are binaries or triples like Alpha Centauri. In total, maybe 20 to 25 individual stars. That's it. In a sphere, 10 light-years in radius, centered on our Sun, there are about 25 stars, the nearest 14 star systems in order of distance. Alpha Centauri at 4.24 light-years. Barnard's star at 6 light-years. Wolf 359 at 7.9 light-years. Lalande 21,185 at 8.3 light-years. Sirius at 8.6 light-years. Lewitton 726-8 at 8.7 light-years. Ross 154 at 9.7 light-years. Ross 248 at 10.3 light-years. And several others, all within 10 to 12 light-years. Most of them are red dwarfs. Small, dim, barely visible, even with telescopes. Only a few are visible to the naked eye. Sirius is the brightest star in the night sky. Alpha Centauri is visible from the southern hemisphere. The rest require telescopes to see at all. And these are our neighbors, the closest stars. If we can't reach them, we can't reach anything. Beyond 10 light-years, the number of stars increases rapidly. Within 20 light-years, there are about 71 star systems. Within 30 light-years, about 200. Within 100 light-years, about 14,000. The galaxy contains somewhere between 100 billion and 400 billion stars. Most of them are thousands or tens of thousands of light-years away. The galactic center is 26,000 light-years distant. The far edge of the galaxy is over 60,000 light-years from here. Andromeda, the nearest large galaxy, is 2.5 million light-years away. These distances are incomprehensible. If we can't reach Alpha Centauri at 4.24 light-years, we certainly can't reach Andromeda at 2.5 million. The galaxy might as well be infinite. We see it, we study it, we learn about it. But we're confined to our tiny corner. One star among hundreds of billions, unable to visit the others, unable to explore beyond our immediate neighborhood. Maybe someday that will change. Maybe we'll develop technologies we can't currently imagine. warp drives that bend spacetime, creating shortcuts through the fabric of the universe. Wormholes connecting distant points in space, allowing instantaneous travel. Cryogenic suspension, freezing crew members for centuries so they don't age during the journey. Upload minds into computers, sending consciousness at light speed while leaving biological bodies behind. These are science fiction concepts. Some of them might violate the laws of physics as we understand them. Warp drives require exotic matter with negative energy density. We've never seen anything like that. We don't know if it exists. Wormholes require similar exotic matter to hold them open. And even if they're possible in principle, we have no idea how to create or stabilize them. Cryogenic suspension works for some organisms. Tardigrades can survive being frozen. Some frogs can too. But humans? We freeze tissue and it gets damaged. Ice crystals form, rupturing cell membranes. We haven't solved this. Suspended animation remains science fiction. Uploading minds assumes consciousness is purely computational. That you can copy a brain's structure into a computer and the result is you. We don't know if that's true. Consciousness might not be transferable. The upload might be a copy, not the original. You might still be stuck in your biological body while a digital version of you travels to the stars. That doesn't help you. Every proposed solution to the interstellar distance problem has fundamental issues. Some might be solvable with future technology. Others might be impossible. We don't know yet. So for now, we're limited. Confined to our solar system. Looking out at Alpha Centauri, seeing it in the sky, knowing it's there, knowing we can't reach it. At least, not with anything currently available. That might change. In 100 years, we might have breakthrough propulsion. In 1,000 years, we might have cracked cryogenic suspension or mind uploading. In 10,000 years, we might be a spacefaring civilization, spreading across the galaxy despite the distances. Or we might not. We might be here on Earth, still looking up at the stars, still unable to reach them, still isolated. Forever. There's another angle to consider, the Fermi paradox. If interstellar travel is this difficult for us, it's probably difficult for everyone. Any alien civilization faces the same physics, the same light speed limit, the same rocket equation, the same brutal scaling of energy requirements with velocity. If they're out there, if intelligent life exists elsewhere in the galaxy, they're probably struggling with the same problems. Looking at the stars, wondering if they're alone, calculating mission parameters for interstellar probes, realizing how hard it is. Maybe that's why we haven't seen evidence of alien civilizations. Not because they don't exist, but because interstellar travel is too hard, even for advanced civilizations, even for species millions of years older than us, with technologies far beyond ours. Maybe the distances are a barrier nobody can overcome. Maybe every civilization is confined to its home system, isolated, unable to reach out, unable to visit neighbors. Looking up at the stars and seeing the same thing we see. Distant lights. Unreachable. Forever beyond grasp. That would explain the great silence. The fact that we've listened for radio signals and heard nothing. The fact that we've looked for signs of alien megastructures and found none. If nobody can travel between stars, then every civilization develops alone, lives alone, dies alone, never making contact. never knowing if others are out there. Just isolated islands in an ocean of darkness. That's a lonely picture of the universe. But it might be accurate. The distances might be the great filter, the barrier that keeps civilizations apart. Not hostile aliens, not self-destruction, not lack of technology, just distance, pure, insurmountable distance. 4.24 light-years to Alpha Centauri. That might be the number that defines our existence. The gap we can't cross. The limit we can't exceed. The boundary of our future. It's not just a number, not just a measurement. It's a barrier that defines our existence. A gulf that separates us from the rest of the universe. A reminder that we're alone in the most literal sense. Surrounded by stars we can never reach. Confined to a tiny corner of space. Isolated. Perhaps forever. But here's something worth considering in all of this. The distance to Alpha Centauri, as daunting as it is, also represents something beautiful in a strange way. It represents the scale of nature, the vastness of the cosmos. The fact that the universe is bigger than us, bigger than our ambitions, bigger than our capabilities. For most of human history, we thought we were at the center of everything. The Earth was the center of the universe. The sun and planets revolved around us. The stars were lights on a celestial sphere, close enough to reach if we could just climb high enough. We were important, central, the focal point of creation. Then we learned the truth. Earth orbits the sun, not the other way around. The sun is one star among hundreds of billions. The stars are unimaginably far away. We're not at the center. We're not special. We're a tiny planet orbiting an ordinary star in an unremarkable region of a galaxy that's one of trillions. That was humbling. It punctured our cosmic ego, showed us our true place. Small, insignificant, peripheral, but it also gave us perspective. Understanding that we're small doesn't diminish us. It contextualizes us. It shows us what we're part of. A vast universe operating according to physical laws that don't care about us, that existed billions of years before we appeared, that will continue billions of years after we're gone. The distance to Alpha Centauri is part of that perspective. It shows us that the universe isn't built for our convenience. The stars aren't arranged for easy access. The speed of light isn't negotiable. The laws of physics impose limits we can't overcome just by being clever or determined. Nature doesn't bend to accommodate our wishes. We have to accept it as it is. Work within its constraints. Find meaning and purpose despite, or perhaps because of, those constraints. And there's something profound in that. We're capable of understanding the universe, even though we're tiny parts of it. We can measure the distance to Alpha Centauri precisely. 4.24 light-years, 25 trillion miles. We can calculate how long it would take to get there at various speeds. We can design theoretical missions, model propulsion systems, estimate costs and risks. We can look at Proxima b and determine its mass, its orbital period, its potential habitability, all from 25 trillion miles away, using nothing but light and mathematics. That's extraordinary. We're specks of organized matter on a small planet, yet we understand the cosmos. We decode the messages carried by photons that traveled for years to reach us. We peer across the void and make sense of what we see. We're conscious beings contemplating our place in something vastly larger than ourselves. That ability, that consciousness, that curiosity, it's rare. Probably extremely rare. The universe is mostly empty space and mindless matter. Atoms colliding, stars fusing hydrogen, galaxies rotating, all following physical laws mechanically. No awareness, no appreciation, no understanding. But here on Earth, and possibly on a few other worlds scattered across the cosmos, matter has organized itself into forms capable of thinking, capable of asking questions, capable of looking at Alpha Centauri and wondering what's there. That's precious. That's worth preserving. Even if we never reach Alpha Centauri, even if we remain confined to our solar system forever. The fact that we can understand the universe, appreciate its beauty, contemplate its mysteries, that alone gives our existence meaning. We don't need to conquer the galaxy. We don't need to spread across 1,000 star systems. We just need to continue being what we are. Conscious, curious, capable of wonder. And maybe, just maybe, we'll figure out how to reach Alpha Centauri someday. Not soon. Probably not in our lifetimes. Maybe not for centuries. But someday, if we survive long enough, if we keep developing technology, if we maintain our curiosity and our will to explore, the distance will always be 4 light years. That won't change. But our ability to cross it might. And if we do, if we send probes or ships or humans to Alpha Centauri, it will be one of the greatest achievements in human history. Crossing the interstellar gulf, reaching beyond our solar system, touching another star. That would be monumental. Not because of what we'd find there. We might find nothing but rocks and radiation. No life. No habitable planets. Just an ordinary star system with no particular significance. But the journey itself would matter. The fact that we did it. That we overcame the distance, the engineering challenges, the cost, the risk. That we refused to accept isolation as permanent. That we reached out across the darkness and made contact with another star. That would be meaningful. A testament to human capability, human determination, human refusal to accept limits. But even if we never do it, even if the distance proves insurmountable, we'll still have learned something profound. We'll have learned our limits. Learned what's possible and what isn't. Learned that the universe imposes constraints that even intelligence and technology can't overcome. That's valuable knowledge too. Humility is valuable. Understanding our place, accepting our limitations, working within the boundaries nature sets, those are important lessons. And maybe they're the lessons we need most right now. We live in an age where we believe technology can solve anything. Where we assume every problem has a solution if we just try hard enough. Where we think human ingenuity is unlimited. But the distance to Alpha Centauri says otherwise. It says some problems might not have solutions. Some barriers might be permanent. Some dreams might remain forever out of reach. Not because we're not smart enough. Not because we're not trying hard enough. But because the universe says no. And when the universe says no, we have to listen. We have to accept it. We have to find meaning and purpose within the boundaries we're given. That's the real lesson of Alpha Centauri. Not that we should give up on interstellar travel, but that we should be realistic about it, honest about the challenges, humble in the face of cosmic distances, and grateful for what we have here. On Earth, our only home, the one planet where we know life exists, where we know consciousness has emerged, where we know there's beauty and meaning and purpose. That's enough. It has to be enough, because it might be all we ever have. Thank you for joining me on this journey tonight. If you found this exploration thought-provoking, a like or subscribe would mean a lot. It helps the channel keep making these deep examinations of our place in the cosmos. And remember, the next time you look up at the stars, they're farther away than you imagine. Much farther. The universe is vast. We are small, and the distance between us and the next star is worse than you think. Good night, and may you never see the stars the same way again.